let's try to compute 6 times 37. And I'll show you one way of doing this, and then in future videos we can look at other ways of doing this and think about why this is actually working. So what I like to do, and this is often called the standard method, is take the larger of the two numbers. It doesn't matter if you're doing 6 times 37 or 37 times 6. They equal each other. 6 times 37 is the same thing as 37 times 6. So what I like to do is I take the larger of the two numbers and I write it on top. So I'll write 37. And then the smaller of the two numbers, which is 6, I'll write it on the bottom, and I'll align it by the correct place. This only has one digit. It's in the ones place, obviously. So I can write the 6. I can write the 6 right over here, and I'll write the multiplication symbol like that. And this is just another way of expressing 37 times 6, which is the same thing as 6 times 37. Now, what we do is we go with the first place in this lower number, and there's only one place here. It's only the number 6 right over here. And we're going to multiply that times each of the digits up here. So first we will start with 6 times 7. So we're going to first multiply 6 times 7. Well, you remember from your multiplication tables, 6 times 7 is equal to 42. Now, we don't just write 42 here, or at least not in the standard method. We wouldn't write 42 here. We'd write the 2 in 42 in the ones place. So we'd write that right over there. And then we'd carry the 4 in 42 up to the tens place. Now, we need to think about what 6 times 3 is. What 6 times 3 is. Well, once again, we know 6 times 3 is equal to 18. But we can't just write an 18 down here. We still have this 4 to deal with. So 6 times 3 is 18, but we've got to then add the 4. So 6 times 3 is 18 plus 4 is 22. So it's 6 times 3, and then we're adding that 4 right over there. And that's how we get our answer. So 222.
But if most people were to see, let me draw a tree here. So that's a twig right over there. Maybe I'll draw some leaves. So if most people, so that is, and let me draw the apple over here. So this is the apple right over here. So for most people, if I were to kind of snap this twig right over here, it's completely common sense. The apple would fall. And if most people were to observe that, they would just think it's a normal happening in the universe. But for Isaac Newton, at least on that day when he observed that apple, he says, well, why did that apple fall? And this, to some degree, is a great example of out-of-box thinking. Because something that for thousands of years, or tens of thousands of years, human beings had taken for granted, just because that's the way it always was, he actually asked the question, why? Does it always have to be that way? And that question took him down an entire line of reasoning that set up the basis for all of classical mechanics, which for the most part we still use today. It's been tweaked a good bit by this gentleman in the last 100 years. But for most purposes, when we're engineering things or dealing with things on the surface of the planet, and we're not going close to the speed of light, we can still use the mathematics that Isaac Newton came up with from this simple question. And not only was he able to kind of think that there's something that might be pulling, somehow acting on this apple, bringing it to the earth, but he actually formulated an entire, I guess, law around this thing. So as you can imagine, the thing that Isaac Newton believes brought the apple to the earth is gravity. And he formulated the universal law of gravitation, or the law of universal gravitation, either way. And in it, he theorizes that the force between two objects, and it's a vector quantity, it's always going to attract the two objects to each other. So the direction is towards each other. The force of gravity between two objects is going to be equal to this big G, which is really just a number. It's a number, and we'll see in a second that it's a very small number. Maybe I'll write it there. This is a small number. I'll give you that number in a second. It's equal to this constant, this universal gravitational constant, which is a super duper small number, times the mass of the first object times the mass of the second object, divided by the distance between the two objects the distance squared. So this is distance between between both of those two objects. So if you're talking about the force of gravity on Earth, this right over here, you'd pick one of the masses to be Earth. So this mass over here, if you were talking about on Earth, you'd pick one of them to be Earth. This is the object that's on Earth. Maybe it's me. And then this is the distance from between the center of masses of both of those objects. So between the center of me, and I won't go into the detail of that, I'll make a more detailed video on center of masses, and the center of the Earth. So it's roughly the distance from the surface of the Earth, or if I'm about 5'9", about half of that distance of, I guess the distance from my belly button about to the center of the Earth is this number right over here. So right when you see this, before we even talk about me and an Earth, or needles and Earth, or taxi cabs and Earth and that force of gravity, something bizarre might be raising up in your brain. You might say, wait, the way gravity is defined by Isaac Newton, or this formula that we're given right here, it's saying that we have gravity between any two objects. And you're saying, look, I'm looking at a computer screen right now. So you're looking at a computer screen right now. And let me take my best attempt at drawing well, this is an old school computer, not a flat panel, but gets the job across. So you're looking at a computer screen right now. How come you aren't attracted to the computer screen? How come it doesn't fly into your face? And the answer there is that this number is really small. And there actually is some force of attraction between you and the computer. It's just that it's more than overcompensated for the friction between the computer and the desk, the friction between you and your seat, and which is frankly being caused by the force between you and the Earth, the force of gravitation between the computer and the Earth. That both of you and the computer are such small masses that you really can't notice it. It's really negligible, and it's being overpowered by other forces that are keeping the computer from even drifting into your face, or your face drifting into the computer.
The present tense is how we talk about things that are happening in the present moment. Like, I eat a donut. If I say that, if I say it that way, it means it's happening right now, in the present, as opposed to happening later, in the future, or before now, in the past. The present tense is what's happening right now. If you can just imagine, just put the words right now at the end of anything that takes place in the present. It should work. I eat a donut right now. Louise doesn't want a catapult right now. The water is super cold right now. Bertie is singing in the shower right now. All of these sentences are taking place in what we call the present. There are a couple of ways to form the present tense, and I've demonstrated two of them here. So we can say, eat, or doesn't, or is, but we can also say is singing. So when you generally have something that has is and ing in it, it means it's happening right now. It's happening in the present tense. So yeah, those are two of the ways to form the present. Is if the verb is kind of unadorned, if it's kind of plain, I eat a donut, not I was eating a donut, or I ate a donut, or I will eat a donut, just I eat a donut. If it's just sort of on its own, like this, it's probably going to be in the present tense. Likewise, if you see the word is and then ing, that also means it's in the present tense. That's what you got to know about the present tense. It's happening now. You can learn anything. David out.